Good afternoon, everybody. My name's John Chelsom. Two apologies. One is my Ukrainian is not too good, so I'm going to speak in English. The other is that I thought we started at 2:30, but we start at 2. So for me, we're starting early. For you, we're starting late. But let's see what we do. So what I'm going to talk about is some of the work that I've done in artificial intelligence over the years, and some of the work that we're planning to do here in RIVNE, starting now, and you'll see at the end, with a bit of luck, for the next 6 years here. Now, at the beginning, yeah, right, just a minute. Okay. I was planning to do a bit more on the history of AI, but I didn't have time because I thought we started at 2:30. So I'll just tell you about this. For many people, the beginning of AI was here with Alan Turing in 1950, asking the question, can machines think? To which the answer was, in those days, no. And he created what's now known as the imitation game, the Turing test of artificial intelligence. And actually that paper that you can read, which is quite easy to understand, the imitation game is actually quite a clever game, because you'd imagine at first reading that it's put a computer in one room, a human in another, talk to them from outside the room, and if you can't tell the difference, then you've created an artificial intelligence. But actually the Turing test is a bit more subtle than that, because in order to fool the human into thinking that the computer is a human, the computer should deliberately make mistakes. So, for example, if you ask the computer to add two very large numbers together, instead of instantly coming back with the answer, it should take some time, so that you think, oh, it must be a human, because it's taking some time to work it out. So some of those deliberately wrong answers, the sort of mistakes that humans might make, if you're playing the imitation game, the computer should be trying to be as dumb as the human to fool you into thinking that it's really human. So that's the beginning for many people. Actually, the beginning for me is 1943. McCulloch and Pitts made a first model of the central nervous system. So they made a statistical model of the central nervous system. In 1958, Frank Rosenblatt created a thing called the perceptron, which was the first computer simulation of what we'd now call an artificial neuron. So the point I'm making here is that the history of AI is long, and the history of AI also is wound up in medicine. So a lot of the early innovations in AI have come along with AI either applied to or directly as a result of advances in medicine and healthcare. So in the 1970s, for example, when AI was in one of its AI winters, nobody is much interested in it. In the Stanford Knowledge Labs in California, they created an expert system called MySyn, and that's a rule-based system. And for many years, that was the most famous bit of AI. The first chatbot, Ed Feigenbaum's Eliza, was what's known as a Rogerian psychoanalyst. So you could ask it questions, and it gave you some psychoanalysis. That, again, from the late 1960s, early 1970s. So that the sort of the concepts and doing it not very well have been around for a long time. So my entry into this field is the 1980s. It is hard to believe, but in the 1980s, there was as much hype around knowledge-based systems and expert systems as there is now around generative AI. So my PhD thesis was building that thing. It's a not very good reproduction from my PhD thesis of making Bayesian belief networks. So these things, and using statistical and probabilistic propagation of belief through networks to make relatively simple diagnosis of disorders of acid-base balance. The problem in the 1980s was that to train your models, and indeed to operate your models, you needed some digital health data, and there wasn't very much. So most record keeping in healthcare in the 1980s was still done on paper. So you had to go far and wide to find some digital health data to train your models. So I found some in Finland. This chap, Arno Kari, in the late 1980s in Kuopio in Finland, the intensive care unit was one of the few places in Europe where everything was fully digitized. So all the information on the patients in the ICU was available on a computer and as digital information. So I was able to use their data to train my probabilistic model, and I created a system which passed the Turing test. So I claimed it was an artificial intelligence. The reality was probably it was an artificial stupidity. It wasn't. You couldn't claim it was intelligent as the human doctor. You could say it was as stupid as the human doctor, made the same mistakes as the clinician made. And here's one of the points of AI is, do we need it to be the same as humans? I don't think so. We want it to be better than humans. Because if it's just as good as humans, then we're slightly missing the point. Its only use is to replicate the imperfect human, and if we don't have enough humans around to make clinical decision-making decisions, we use the computer instead because we can replicate that as much as we like. What we want is something that's better. So making a computer, an artificial intelligence which passes the Turing test is not necessarily sufficient as a finishing point. So after my PhD thesis, I stopped doing AI in medicine. I moved to do AI in something else for two reasons. One is because of this, what Arno Kari told me in his ICU. He said, look, John, you can make your computer as clever as you like, but, and by and large it wasn't very clever then, you can make it as clever as you like, but when I walk into the unit in the morning, I can just tell by looking at all my patients whether they're getting better or whether they need my attention, and I don't need to look at any charts or data. My instinct, I can just tell. And however good your artificial intelligence is, it'll never be able to do that. And for quite a few years, I used to give that as an example of the limitations of AI. We'll come back to that in a second. The other reason I stopped was to do with ethical dilemmas in artificial intelligence, which were the same dilemmas then as they are now. The ethical dilemma from a software engineering point of view is that if you make an AI which recommends to a clinician to make a clinical decision and the AI gets it wrong, and the clinician's not in the loop, so it's automated decision making, then the person that gets sued is the software developer, the software engineer, the company that provided the AI. If you keep the clinician in the loop and the clinician trusts the AI, but the AI makes a mistake, the clinician trusts it, then the person who gets sued is the clinician. It's the clinician's fault for believing the silly AI. So that's a problem. Problem coming the other way. There's a well-publicized piece of case law in the 1980s related to the use of AI, but actually case law going back to the 1920s in America, where there's a tugboat called, I was going to have some slides on this, I didn't have time to put it. There was a tugboat called the TJ Hooper, which was hauling some cargo up the east coast of America, and it wasn't fitted with a radio. So when the storm hit and the tugboats and the cargo was sunk, the owners of the tugboats got sued by the owners of the cargo for saying, if you had had a radio fitted, you would have been warned of the storm and we wouldn't have lost our cargo. And the fact that that case was settled in favour of the cargo owners set the precedent in the US that if there is a technology available which is demonstrably better than what you've got at the moment and you don't use it, then you can be sued for not using it. So as far as AI is concerned, as far as I could see, you were damned if you do and you're damned if you don't. If you don't use AI and it's better than humans, you'll get sued. If you do use it and it makes mistakes, you'll get sued. So that is, for me, is the biggest ethical dilemma, which has not gone away. Right. So where are we today with AI? I was going to fill in with lots of examples of how AI between the 1980s and up to the current era of generative AI has been quietly working away doing stuff. So things like robotic surgery started in the late 1990s. A lot of surgery now routinely is done either by or with the use assistance of robots. That's all AI driving that. In interpretation of diagnostic imaging, so looking for example, fractures or lesions, the interpretation of diagnostic images has been so good with AI for such a long time that the profession of radiologist, human interpreting radiological diagnostic images, is under threat, because what's the point of training to be a radiologist if the computer is going to be better than you, which it is demonstrably in lots of cases. The example I've got here is on drug discovery. This is just recent in the regular press of headlines of MIT using AI to discover new compounds and targeted at specific bacteria to kill them off. And that's been common for the last 10 plus years for using AI for drug discovery and trialing new drugs. There's lots of examples. If you go to your sports centre or cinema or around the supermarket, you quite like to see a defibrillator on the wall. The defibrillator is packed with AI. So someone cardiac arrest, anybody, trained or not, can pick the defibrillator off, open it. First thing it does is it starts talking to you, tells you what to do. You put the paddles on, and the ECG is read, and that's then interpreted using AI to determine whether it's worth shocking the patient or not. Because if you shock the patient and they're not, their heart hasn't stopped, then shocking them is going to stop it. So it's not necessarily collapse, get the defibrillator out, shock them. If you do that the wrong way, you'll be killing them. So the AI is working out whether you should shock them or not. So that's, again, routine standard fare in healthcare to use AI behind the scenes. Been working for years and years. So let's get up to the present day. I used to give talks saying, Mano Kari, your AI will never be able to just look at a patient and tell whether they're getting better or not until this. So this is in my hometown of Oxford and at the university there. This from 2014. So video cameras trained on patients, and just from the video image, nothing else, they then were able to read heart rate, respiratory rate, and body temperature just from the video image. Since then, so that's Leonid Teroshenko and Mauricio Villarreal, they have taken that on now, so that first to neonates and added oxygen saturation. Currently, according to Mauricio, which is, I don't think it's published yet, there's a football ground in London, a Premier League club, where they have cameras following every single player doing this, so reading vital signs of every player on the pitch, well, presumably for the club whose ground it is, not every player, half the players on the pitch, following their vital signs, continuous monitoring of respiratory rate, heart rate, body temperature, oxygen saturation for every player on the pitch. So without obviously any intervention. Let's get a bit more down to earth of what seemingly seem easy things to do. Things called care pathways. So in healthcare, the treatment of patients, the best treatment of patients, particularly when using digital health systems, you can use what's known as an executable care pathway. So a set of guidelines for what's the next best thing to do in the care of this patient. So the care pathway is that structured plan of how to treat and manage a patient, and that's good. How a care pathway is made. Come on to that in a minute. The trick is to make your care pathway executable. There's an executable care pathway. And we can see that that's a bit like a knowledge-based system. So your electronic health record system with all the patient's information held digitally uses the care pathway and the current observations to decide what to do next. Except that decide what to do next has been worked out as a procedural set of steps, really, if this, that, and the other with the patient. So if the patient's overweight and not getting enough exercise and got bad diet, then give them some advice and tell them to get their BMI down, etc. would be simple advice which could be given in a care pathway. So if you contrast that with what's happening at the top, that's clinicians thinking, they're taking observations, combining their clinical knowledge with the observations, doing some reasoning, and reaching decisions about what to do next in the care of the patient. You could say that your classic AI, which includes probabilistic Bayesian inference, rule-based systems, ontologies and description logic reasoning, is doing this, is taking those observations, replacing the reasoning of a clinician with some sort of reasoning engine, taking some knowledge base, and then, to stop yourself being sued, providing decision support to clinicians who take the action. If you get this wrong, it's this green chap's fault, not my fault in getting my reasoning engine wrong. If you look at generative AI, very similar, except there's no reasoning going on. And there's another ethical dilemma. So generative AI, highly simplistically, is pattern matching. I put a pattern of inputs and I get a pattern of outputs. There is no reasoning going on, so I can't ask the generative AI why. So next best action is this, why? Well, I can't ask it, but if I ask it why, it will tell me. It'll generate something else, an explanation of why that was the next best action. And I can go round and round doing that, and it looks as if it's going through a reasoning process, but it's not. So there's another ethical dilemma. If it looks as if it's reasoning and giving me explanations of what it's doing, and it's not actually doing that, is that acceptable? Would I prefer some algorithm or AI which is genuinely going through a reasoning process? Because generative AI is working at the level of the neurons and the artificial neural networks, doing what we're doing, and replicating our higher level function of reasoning, but without actually doing the reasoning, or is it? That's the ethical question there. Anyway, for today we don't mind. So how do we make one of these executable care pathways, which I was talking about? We use evidence-based medicine. So here's a pyramid of evidence on what's good to do in making clinical decisions. And there's lots of very low quality evidence. We can call that the web or the internet. So in there, you'll get some good stuff. So you go to WebMD and get lots of good advice. In there, you'll find people saying you can treat COVID by drinking disinfectant. So you get all sorts of rubbish at this level. So, okay, there's some good stuff there. There's lots of bad stuff there as well. As you go up the pyramid of evidence, you get better and better quality of evidence. And the stuff at the top are what's called meta-analysis, where you get multiple randomized controlled trials which have proved that a particular drug or treatment or approach is better than another through a properly conducted randomized controlled trials, more than one of them. So that's like your gold dust of evidence, if you can base it up there. From this evidence base, the best evidence is used to decide what is clinical best practice, and those guidelines are published, and they're published as documents. They're not published as flowchart. Well, sometimes they have been, but not as flowcharts or anything executable. They're descriptions in text, narrative text of what's the best practice. However, you can read, as a human, your narrative best practice and make a flowchart of what to do. So here's a flowchart and a UML, Unified Modeling Language Activity Diagram. So you can make this, and this is a simple care pathway. Let's do a lifestyle assessment. We'll measure the height and weight of the patient, calculate their BMI, body mass index, and depending on what their body mass index is, do certain things. So just give them a bit of advice, or actually make some intervention. If they're underweight, nastily do some diet and strength. If they're overweight to an unhealthy degree, then again make an intervention. So that's a very simple care pathway drawn as a UML activity diagram, but this is now in software, so we can save that and do this. So draw our activity diagram, save it in XML form, process it, turn it into an ontology. That's all our only reference to ontologies today. Turn the ontology into the template for an executable pathway. Load that executable pathway into your electronic health record system, and then you get a system which is guiding you through what to do next, all based off the activity diagram you drew. So that's sort of good, but you have to draw the activity diagrams. Or do you? So here's some more work about to be published, so presented at conference, not published yet, by using generative AI to draw the UML diagrams. So take the textual description of best practice, ask the AI, generative AI, to generate a description of what the UML diagram is, and then generate the UML diagrams. So there's a language called plant UML, which is basically a coded language, a declarative language explaining what UML diagram to draw. And because that's declarative, you can generate those instructions by prompting generative AI to draw the UML diagram. So what this paper does is take quite a complex care pathway and compare a human sitting down and drawing the care pathway as a UML diagram, and various other flavors of generative AI and large language models to do the same. And the best performing, which I believe might have been Claude, I don't remember what it says there, that one. Some perform better than others, basically. But in the evaluation, there was at least one which was pretty good at doing this, bearing in mind it's early days. So the prospect is that you could take a narrative guideline, give it to generative AI, ask the AI to draw a UML activity diagram, then you've got that, because here's your process, and then make it executable, and then tell clinicians what to do next in the care of the patient. Right, so now we arrive in RIVNE. So I'm here for the month of August, trying to get together the second phase of this European project. So this is a European project which has just finished literally a few weeks ago, called Watching the Risk Factors. And the idea of this EU project was to have an app for citizens, where you can enter some data in the app, fill in questionnaires about what you're up to. It takes data from personal devices, so Fitbit, if you're using devices to monitor, for example, if you're diabetic, devices monitoring your glucose levels. Any data from your personal devices also comes in here. Data from your health record to come in, actually not in this version, so that wasn't in this version, but send the data from here and from those to AI generated advice, and that for what's known as non-communicable diseases, so melanoma, diabetes, cardiovascular disease. So based on your information, here's your risk. So everything's fine, you're not at risk of any of those diseases, or you've been out in the sun a lot and you don't seem to be wearing protective sun cream, your risk of melanoma is going up, or your diet's appalling, you're okay at the moment, but you're at increasing risk of diabetes or coronary heart disease. So those risk factors come back reported. Now that's an interesting use of AI, because you sort of get around some of the ethical problems there, because you're not making a diagnosis or a treatment, you're just alerting people that your risk level as calculated by the AI is increasing. Now, you might get that wrong, but getting it wrong is probably not the end of the world. It's sort of useful advice. If it's reliable, then you're doing something useful. So that project's finished. New project, this one, is under proposal. So this project, we don't know if we'll be successful in this, but if we are, it'll start this time next year. And this involves 3 partners from RIVNE, so the University Nui, the regional hospital, and 100% Life NGO in RIVNE. And the idea here is to extend the original WRIFA project to extract data from healthcare systems, so primary and secondary healthcare data is coming in to be used in the training of the large language models for the AI advice and for providing personalized advice. Still data from personal devices, so your Fitbit and everything else, and from research databases. So some countries have already collected lots of data on patients, anonymized it, made it available for research purposes. So data extraction, and then the advice is to make what's known as federated AI. So there are 5 countries involved in this next version of WRIFA, including Ukraine, and the idea is to extract the data in all those countries and build large language models specific to the data from each of those countries, but also aggregated together. So the AI advice is based on learning specifically for each of these and each of these collectively. And federated architecture means that these large language models can be trained and run in their country of origin, which is sort of a good thing, because even in the EU, with its rules and regulations and protections, it's difficult to move identifiable patient information from one country to another. If it's anonymized, fine. If you can identify the patient, it becomes much more difficult. So an architecture which does this in this distributed way needs to be trained on anonymized data. And it could be done like that, but because it's federated, we could put it all in what's known as an AI factory. So the EU is busy funding AI factories, and there's already a fair number running. These are massive data centers with huge computing power of GPU power sufficient to train large language models. And if you're doing European research project, the use of those AI factories is free. Well, it's paid for by the EU, but free for the use of the researchers. So the idea in WRIFA is that we'll use these AI factories. Except slight problem, that there's Ukraine, and it doesn't have an AI factory, and it's not in the EU either, but can participate in European projects. In the other countries, participating countries, Norway doesn't have an AI factory. Finland does. Somewhere in there is Spain, that does. So not all the countries involved in the project. Ireland is another one. It's there. It's not even. It's in the EU. I don't know. They seem to have done something wrong in this. It's not hosting AI factory. But what we can do is, using an AI factory, put all the federated models in one place. So we can put them all in an AI factory in Germany, which is where we'll start. We've got our own AI factory, not funded by the EU, in Ireland. So the training of the large language models done in one place potentially could be distributed across all these countries in the future. Last bit, I think, the opportunity in RIVNE first to participate in this project. Of course, we hope that we win the proposal for this, but there's nothing certain. But there's stuff we can do regardless of whether we win the project or not. Now, one of the issues in a 5-year EU project for training AI is that really we need data on the first day of the project. So if we start a project for 5 years and then do all the necessary, which I'll talk you through here, to get the data to train the AI, it'll take us at least a year, probably longer than that, just to get the AI and the data in the first place. The data fuels the AI. So in RIVNE, we've trying, and I think we will succeed now, to get a project underway to get the data before the project starts. So in the primary care, running medical information systems to take data off those systems and put them through what's known as an integration engine, which is running in the regional hospital, and put that into a repository. The current trendy thing to call that is a data lake, so a big repository of information, plus information from the electronic health record running in the hospital and other data like labs and imaging, to store all those data together. The opportunity here for telemedicine is that telemedicine devices, which are difficult to integrate with the health record system, we have found a way. In fact, one of the people who found a way is sitting right here, Danilo. Last summer, we proved that we can take data off telemedicine devices and put it through this route and get it into the health record system in an automated way. Once the data are in there, then this thing here is in charge of transforming the data into whatever form you need to drive the AI, anonymizing it, because we need to use not anonymized data for training, and making sure that the patient consents to us doing that. So that's a big bit of the rules and regulations about using patient data for anything. Patient needs to consent to it, actually, unless it's fully anonymized. So in most countries, and I'm not sure I necessarily agree with this, but most countries' legislation says that if you fully anonymize patient data, you can use it for whatever you like without asking the patient about it. There are lots of ethical dilemmas, I think, involved in that one, but that's current state of play. There's also encryption in here, because some of those data we do want to use to provide personalized advice to individual patients. And so we have to be very careful that, having put the data for thousands of patients in here, when we take it out, a piece of those data to use for an individual patient and give to their app that they're running on their phone, that we got the right patient there. So we don't want to be giving you your friend's data to give advice for yourself. So by encrypting those data using patients' public key, for, I don't know how many people know about public key infrastructure and encryption, but encrypt with the patient's public key, send it to their phone, decrypt it with their private key, only that person has the private key, you can more or less guarantee that if the person using the phone properly authenticated is the same person as the data which is coming out of this store. So that's our challenge now in the next year, is to get this up and running in RIVNE before our project starts next September in the EU. And the sort of advantage to do this, if we're unsuccessful in the EU bid, then we'll have this anyway in a year's time to use for other things. That's the end, except to say last March, so actually April 2026, we ran a week-long course in Oxford. This is my college in Oxford, St Edmund Hall, the University of Oxford. Last year we had 24, I think, people came from RIVNE to attend that, including at least 3 people who I can see in the audience today. Our intention is to run that every year now, and hopefully even increase the number of people coming from Ukraine to that. It's a sort of not quite a conference, workshop and thinking session. So those are the dates for next year. There's some background information on some of the things I've been telling you about, and these activities at St Edmund Hall are part of a global initiative called Global Open Source Electronic Health Records. Right, that is it. Questions are welcome. Yeah, thank you. Thank you for listening.
Could you open the 19 slide? Because I have a question regarding the this primary care building or organization, and so, for example, how difficult is to collect this data from these organizations?
From primary care?
Yeah.
Occasionally it's quite easy. Often it's extremely difficult.
Yeah, but so I know that our system, like health system, usually stores a lot of data in archives, in paperless, like in paper mode. So they are not digitalized, and so it could be quite difficult to maybe receive this data from those.
Yeah. And the starting point for all of this is that you need to have the data in digital form. So if the health record is on paper or partially on paper, then it doesn't work. There's sufficient digital information systems in Ukraine to get enough data to do this. But here is fairly near the start of the journey, towards a fully digitized health system. And just as in every other country, every country in the world, there's a divide. So if you're there's a divide on wealth, there's a divide of where you live. So if you're wealthy living in Kyiv, you've probably got an electronic health record. If you're not wealthy living in a rural village, you're unlikely to have an electronic health record. That's the same everywhere in the world. I mean, in America.
Yeah, that's right. And also, so if some people are living in rural region, and for example, there could be a less educative personnel or have less opportunities to help people. And for example, how do you differentiate the data and aggregate this into one system, because they have a different maybe quality of the data.
Yes.
Yeah, so that could be some of the concern here.
There are a lot of issues, so I'll just talk about a couple that you've raised there. I first came to Ukraine in 2018 with the World Bank to look at strategies for rural telemedicine, which addresses one of your issues there, would address, were implemented, which is that in rural areas, people go to a Felsher station, maybe there's a Felsher comes around once a week, and having telemedicine where the Felsher can connect to expertise in a district or regional hospital or even at national level would considerably help with healthcare of patients without them having to leave the village. And all those data that are recorded in such sessions will then be an electronic health record. But that's still that's an ongoing challenge to do that. The other thing about if we do have medical information systems with sufficient data stored, first is what's the quality of the data in there. So you can have an electronic health record with unstructured data in. The more structured the data, the better the quality is likely to be. And here's actually where generative AI may, if we're not careful, take us backwards, because the last 20 or 30 years of development of electronic health record systems has all been moving to more and more structured electronic health records, rather than just typing in a letter or a clinic note. The ethical dilemma now is, if I've been doing that as a doctor for the last 30 years, now I can get generative AI to read my unstructured note and do something with it. But what generative AI currently isn't doing, a project starting to try and solve this problem, is turn the narrative into a fully structured electronic health record. So data quality depends on how structured and guided you are in putting that in. The next thing is, this is a piece of software, an interface adapter, can you get the data out of there so that you can put it in here?
Yeah, of course. And also the next question is, how do you encrypt this data between these systems? Yes. I know that there's an interface or the protocol, the H7, yeah?
Yes.
So it should be the widely spread protocol between to connect the systems. Yes. And also I know that so this data lake, and you have the anonymization, which is happening after the data lake. Why? Yes.
Because some of the data that we want to use from here, we don't want to anonymize. We want to use it for specific.
Yeah, so it does contain the names of the patients and all the personal information. Yeah.
But this is all inside the regional hospital, so it hasn't gone anywhere. Okay. So it's as safe as if it had been here or in there. It's still within the confines of the hospital. The reason that's shown as multiple instances of the data lakes is that the hospital own the data that's in there.
Okay,
they don't own the data that's in there. So though this is hosted in here, depending on data sharing agreements, they may be in separate repositories. Now, the other thing on the interface adapters, you mentioned there are some standards. There's a standard particularly called HL7 FHIR, Fast Healthcare Interoperability Resources, which all of these interfaces, there's an example there, HL7 FHIR. If you build your own interfaces, you can use that standard, and it's a good standard and a protocol both for the structure of the data and functionally how you exchange it. How do you do RESTful web services to exchange the data? Problem is, if you go to one of these, it almost certainly doesn't have an HL7 FHIR interface. Yeah, it might have an API interface, or it might have no interface at all. That's why you have to build the interface adapter in the best possible way. So there's a technical issue, and then there's an issue of the vendor of that system. So if they don't want to cooperate with building interfaces, it's not impossible, but it becomes difficult. So best case scenario, if you've got an MIS with sold by a company that wants to interface and has built an API to their system, then that's relatively straightforward. If they've built an API to the system, in lots of countries, they'll say, we've got the one, switch it on. I mean, in my hospital in Oxford, switch on an interface, one interface to the hospital EPR system $100,000 for that just to switch it on. It's a bit like I've got Microsoft Windows and I want to upgrade to Windows Pro.
That's also a problem.
yeah.
There's a lot of hospitals that they have like old systems and
Yes,
they
yeah.
don't want to upgrade or don't have the opportunity to upgrade.
There are other ways to do it. There are lots of technologies which will help you to make interfaces to non-cooperative systems. And there's lots of ways, but they're difficult. So it requires bespoke programming, and you need to do it in a way that if the vendor here really doesn't want you to do it. I mean, you can do things like, oh, we'll work off your backups, or we'll go directly into your database and write our own queries to your database. But if the vendor realizes you're doing that, then next release, oh, we've changed something. We changed the way we do the backups, or we changed some structures in the database. And by the way, we're not publishing the schema to our database. There's all sorts of things they can do to make it more and more difficult.
There's a lot of issues and problems to fix here.
Yes.
Yeah. Okay. So thank you.
Yes. Sorry.
So first of all, thank you for your speech. Nice to see you again here in RIVNE. I have a few questions, and the first one, if I'm getting it right, that every regional hospital needs to have its own data lake for this system.
Yes.
And you know that they need also an infrastructure for this and people for support and all this stuff. So where they need to get all this trained personnel to support this data lake?
All good questions. So if we do the WARIFA project, the infrastructure and then the expertise to do this will come as part of the project paid for by the EU. Tick.
So from EU money they should support it. Yes. Okay.
However, doing it everywhere won't. And of course, we may not win the bid. So that, I mean, it's a good question. It requires expertise and it requires kits to do this. So this needs to sit in a server room. Now, the World Bank paid for a lot of the infrastructure that's at the regional hospital server room and some of the servers and equipment there. Hopefully, the EU can pay for another rack in the server room and some more equipment, but who knows?
Okay, and one more question. So, if my data is stored in my regional hospital and I'm moving to another city or country and another regional hospital, and this data is not anonymized, so how can I transfer my data from one hospital to the another as a patient?
Right. So, depending on which country you're in, there may be national level protocols for doing such a thing. So, for example, in the UK, where I live, there's a nationally defined standard for a full primary care record, and every system that's authorised to work in the primary care practice has to be able to export to that form. So in theory, you can export from one and move it to another in theory, but sometimes theory and practice don't quite match up. At an international level, there's a standard called the International Patient Summary, which is a way of providing a summary record with the important information you need as patients move from one country to another. And it's possible to use the International Patient Summary as a blueprint for how to get a summary record at least that you can then move inside a country. To do things like that, even nationally, requires national level cooperation, development of standards, enforcement in the sense of making sure that systems don't get accredited for use if they're not capable of connecting to the e-health infrastructure. It needs a lot of top level stuff, but it needs not too much top level, because if the government tells everybody this is what you have to do in this way, it's proven over and over in other countries that everything goes wrong. You need people at the grassroots to be given enough freedom to make local solutions and do what works for them, adhering to the national guidelines, for example, a national agreed summary structure so that you can take your health record from anywhere and move it somewhere else in the country. It takes a long time to do that, both at a technical level and as organisational and even legal a basis for doing that.
I don't know how it's in EU, but here in Ukraine, I think we have like national level information system for medical records. So one of the options is to make some kind of synchronization between this and that system. The last one questions, a little bit technical maybe. They're quite not so much open source large language models, and how you choose LLM for your project and how it should be trained. Is this model open source, or are you considering other options?
Okay, so one of the requirements for EU projects is that the products of it have to be as open and reusable as possible. When you get to large language models, there's some issues there. I mean, of course, even if you go to OpenAI, the software running is open source software, so you can take their software, and if you've got sufficient GPU power, i.e. enough money, which is actually what's happening in that picture I showed at Ireland, and what's happening in the EU AI factories, running effectively open source software for. Okay, that's good. Then you train the model, and now you've got a trained model. Depending on who owns that, you can then open source the model. But whoever paid all the money for the GPU to train the model owns the model, and whether they make it openly available or not is then up to them. Then you've got the next problem is, okay, I've trained my model, say, on the OpenAI infrastructure, ChatGPT, etc. But actually now I want to run it on Claude or DeepSeek. Now there are some standards for exchange of large language models between different platforms, which in theory allow you to do that. Again, in practice, it's a bit like if you're a database programmer and you're using SQL, which I call SQL. In theory, you're using an international standard for writing your database queries, but good luck to you taking your database queries from Oracle to MySQL or SQL Server. Largely it's the same, but you can't 100% just take it and put it there. You have to do some tweaking, or at least if it runs, it probably won't run the most efficiently on a different platform. And when you come to large language models, the how efficiently does your model run? It's not just a question of transferring it to a different platform. It then needs to perform. So even if the performance is down by 20%, that's a lot of GPU power that you need it to run it suboptimally. So there's lots and lots of issues about making the large language model portable. That's one of the issues addressed or attempted to be addressed in this project, is to make a federated AI so that you can move the models from one platform to another and you can aggregate them together. It isn't easy to do, and again, the power, if you like, lies in the person who's paid all the millions to train a model. Now it's a valuable resource, so then open sourcing it is quite a big step. Okay, brilliant. Thank you, everybody.